So, in case you guys were worried, this isn't a biochem lecture. You can learn about all the mechanisms when you study that section. My version's more geared towards remembering a few easy rules about the hormones and the cell signaling pathways, lightly touching on mechanisms only when they're needed. Let's start off with an easy rule number one. All lipophilic hormones bind to intracellular receptors. Now when I say lipophilic hormones, which ones am I talking about? For starters, every single hormone made in the adrenal cortex, namely aldosterone, cortisol, and the adrenal androgens, DHEA and androstenedione. How do you know they're lipophilic? Because they're made from cholesterol, which itself is a lipid. By that token, all androgens, including testosterone and DHT, estrogens and progestins, are lipophilic as well. Can you remember the last hormone derived from cholesterol? Hint, we just talked about it. It's vitamin D, and it too is lipophilic. The final lipophilic hormones you have to remember are the thyroid hormones, which are oddballs because they're made from amino acids, not cholesterol. It's also an oddball in that it's the only lipophilic hormone that needs to be actively transported into the cell. Most hormones have intracellular receptors because they can easily diffuse across lipid bilayers. We'll talk more about these hormones later, but that's the most straightforward rule. Adrenal steroids, sex steroids, vitamin D, and thyroid hormones all bind intracellular receptors. Next straightforward rule, all hormones that primarily act as vasodilators do so by either directly or indirectly activating guanylyl cyclase and increasing cGMP in the cells of vascular smooth muscle. But Arjun, says you, did we even talk about vasodilatory hormones? All I remember is how cortisol's no fun to hang out with. Alright guys, looks like I can't pull one over on you, but you can probably think of some. The one everyone's most familiar with is nitric oxide. The other two are atrial and brain natriuretic peptides. They decrease blood pressure by acting as vasodilators and by doing pretty much the exact opposite of what aldosterone does in the kidneys. Unfortunately, that's about it for the quick and easy rules. Here you've got a couple of options. First aid is a bunch of mnemonics to remember the other hormones, but it's a lot of letters, and I always learn better when I get the concept. So, starting with this section, I'm going to take a slightly different approach, keep things nice and simple based on a few core rules. You guys can figure out which approach you're going to follow. We'll start with the meat and potatoes, the anterior pituitary hormones. What's our favorite mnemonic for them again? Flat pig, for FSH, LH, ACTH, TSH, prolactin, and GH. Now, I know those of you who hate mnemonics are going to be tearing your hair out just about now, but this mnemonic has so many applications simply because the flat hormones and the pig hormones have a couple of very important differences. Because it's a long section, pause the video and see if you can remember what the two main differences between the flat hormones and the pig hormones are. First of all, FSH, LH, ACTH, and TSH are all secreted by basophils. Remember B-flat? And prolactin and GH are secreted by acidophils. Second, the flat hormones are all trophic hormones, whereas the pig hormones are not. It's seriously like the stuff conspiracy theories are made of. Now, I'm gonna let you in on another one, and get ready to have your mind blown. As it turns out, the flat hormones all use the same cell signaling pathway. No joke! Every single one of them binds to a G-protein coupled receptor on the respective gland and stimulates adenylyl cyclase to increase intracellular CAMP. To make the coincidence even crazier, prolactin and GH also share a receptor pathway. They bind to the receptor-associated tyrosine kinases. Am I seriously the only one who thinks this mnemonic is crazy awesome? This is an awesome pattern, because even though there are more CAMP and tyrosine kinase pathway hormones than just these, you can use the hormones you've got here to derive the others. I'll try to keep things trim and high yield. Let's start off with the hormones that use the Y kinase pathway. We just talked about prolactin and GH, but what was the other hormone we went over that uses a similar pathway? It's insulin. Remember that slide where I animated the whole... Anyway, there's a pattern that you can see between all of these hormones, and that's signaling rule number 3. The Y kinase hormones are the ones that have significant anabolic profile or a major role in growth and development. The most important examples are the hormones that control the growth and development of the various blood cell lineages. For the white blood cells, you've got GCSF and the various immunomodulators. For the red blood cells, you've got erythropoietin, and for the platelets, you've got thrombopoietin. The other hormone that acts via the Y kinase pathway is growth hormone's little protege, IGF-1, which stands for insulin-like growth factor. Of note, insulin and insulin-like growth factor operate via the slightly different intrinsic tyrosine kinase pathway, Well, the receptor itself acts as the tyrosine kinase, as opposed to the receptor tyrosine kinases which recruit helper enzymes from the cytoplasm. With that many ins, the difference should be intuitive. Nyuk, nyuk, nyuk. I think it's pretty unlikely that she'll be tested on the other growth factors, but you can remember it pretty easily because they sound like insulin-like growth factor. On a side note, do any of you have any idea why tyrosine kinase receptors are more likely to affect growth and development? Without getting too mechanistic, the signaling systems all differ in how they enact change. The G-protein coupled receptors choose to amplify the hell out of their signal, exponentially increasing the number of secondary messengers to achieve a very active response. The tyrosine kinase pathway, like the steroids intracellular pathway, often terminates in the activation or deactivation of transcription factors. You can remember that from the insulin animation slide near the beginning. It's a slower process, but one that's more conducive to the profound changes of growth and development. The rest of the hormones get broken down between the two different types of G-protein coupled receptor: G-stimulatory, which signals via CAMP, and GQ, which signals via the molecule IP3 and an increase in intracellular calcium. The two hormones I consider to be stimulating hormones both use the G-stimulatory pathway. The quote-unquote stimulating hormones I'm talking about are epinephrine at the beta receptors, which makes sense, and glucagon, which is a little confusing until you realize that glucagon is basically used as a substitute for epinephrine when people overdose on their beta blockers. While I'm going to go out on a limb and say that a lot of the signaling mumbo-jumbo is not the highest yield stuff you'll find in the book, it's absolutely essential that you know that epinephrine and glucagon work by the same intracellular pathway, assuming it's a beta receptor, and that they share some similar catabolic effects as a result. By the way, why do I keep specifying that only the beta receptors work via the GS pathway? What about the alphas? Well, we don't have time for that right now, but there's a whole section on pharmacology on the signaling pathways used in the autonomic systems. Check that out once you're done to round out your knowledge. Finally, both the hypothalamic and posterior pituitary hormones are split between the GS and the GQ pathways. How do you remember how to split them? Why, you use First Aid's helpful mnemonic, of course. Before any of you call me a hypocrite, I do like mnemonics, just not 4 different ones where all the letters overlap and there are letters left out, not used. Anyway, the very helpful mnemonic you use for the hypothalamic and posterior pituitary hormones is GOAT. If the hormone's name begins with G, O, A, or T, it uses the GQ pathway. Otherwise, it uses the GS pathway. But Arjun, says you told me that the posterior pituitary hormones were split up and that they're both on their GQ, and to that I say cool your jets, man, because that's only ADH's first receptor, V1. Its second receptor, V2, is actually a GS-coupled receptor. There's a lot of rules, so let's do a recap. The lipophilic hormones go with the intracellular receptors. The vasodilator hormones go with the CGMP-mediated receptors. Of the anterior pituitary hormones, the flat hormones are mediated by CAMP, or the GS pathway, and the PIG hormones are mediated by the tyrosine kinase receptors. The tyrosine kinase hormones are all involved in major anabolism, or the development of blood cell lineages, and insulin and insulin-like growth factor are specifically mediated by the intrinsic tyrosine kinase pathway. Finally, the stimulating hormones epinephrine and glucagon use the G-stimulatory or CAMP-mediated pathway, and the hypothalamic and posterior pituitary hormones are split between GS and GQ. The ones that start with GOAT are GQ, except for ADH's second receptor, which is GS. I'm going to talk briefly about the mechanism by which lipophilic and other steroid hormones act on cells, and why they're so different from the water-soluble protein hormones. The way it works is, your steroid comes riding in on a steroid binding globulin. Why? Because it's not water-soluble. Once it gets to the cell, it can actually diffuse just fine through the lipid bilayer because it's lipid-soluble. So most of the time, steroids act on transcription factors, causing a conformation change that either allows localization to the nucleus or increased DNA affinity. The transcription factor binds to the steroid-controlled regions of the genome, leading to transcription and eventually translation of proteins that cause long-term and structural and functional changes in cells. This is way different from how G proteins and their associated receptors operate. Like tyrosine kinases, steroids and other lipophilic hormones in general are slow to act, but cause long-lasting structural alterations. Whew! Bet you guys are sick of biochem at this point. There are more signaling pathways that are in First Aid, but I didn't mention them because they're either very low yield or better explained somewhere else in the book. But for now, we're going to have some fun with our last hormone that gets a personality, thyroid hormone. Okay, this is a fun one. Unlike cortisol, that was a total downer. The thyroid hormones T3 and T4 are the ones everyone wants to be. They've always got the energy to go out and party, and the metabolism to shred through heinous amounts of beer and nachos they frequently consume. Then you realize, that was you once upon a time. Ladies and gentlemen, I present to you T3 and T4, the college freshmen. First of all, these guys have ridiculous amounts of energy, but how the heck do they keep going? As it turns out, T3 and T4 are potent potentiators of catecholamines at the beta receptors, leading to all the things you'd expect: faster heart rate, increased contractility, and a greater mental subjective sense of energy. Second, as most people wistfully remember, early college was a time when your metabolism seemed like it'd never fail on you, no matter how much junk you ate or how much beer you drank. How do these party animals chomp through all that fuel? The thyroid brothers' crazy metabolism is the result of increased activity of the sodium-potassium ATPase pump, which in normal cells takes up a whopping fifth of the cell's total energy. The breakneck pace of the enzyme generates a lot of heat, but requires increased fuel to support the additional ATP generation that'll otherwise lead to weight loss. The fuel comes not only in the form of mobilized lipids and glucose, but also from increased O2 to support the aerobic metabolism. Finally, college is a time of learning and development, and college freshmen are primarily concerned with developing their ability to think and their ability to bone. Before you get mad at me, by the way, I meant their bones. Their orthobones, not their urology bones. T3 and T4 are important regulators of growth and development, notably the maturation of the central nervous system and of bone growth, which it does synergistically with growth hormone. And for those of you with dirty minds that keep veering towards reproduction, well, actually, thyroid hormone's necessary for normal menstrual function, so there you go. Guess there's something for everybody. Here's a breakdown of thyroid hormone's effects. Increased metabolism takes center stage, which leads to increased energy and O2 consumption. Note that the increased beta-adrenergic activity, which includes increased heart rate, respiratory rate, and nutrient mobilization, will actually work to support the increased metabolism that thyroid hormone causes. It's worth mentioning again that if a hyperthyroid patient doesn't work to increase their calorie intake, they'll tend to lose weight. And as it turns out, most hyperthyroid patients do increase their food intake, but not enough to account for their radically increased metabolism. Weight loss despite increased food intake is a very unique pair of symptoms that should immediately make you at least consider hyperthyroidism. Lastly, thyroid hormone's involvement with tissue development may not fit the immediately obvious picture of increased metabolism and energy, but if my hilarious mnemonic for college freshmen didn't help you remember it, then think back to this slide when we're covering congenital hypothyroidism in the pathology section. Hypothyroidism is well known to cause oligo or amenorrhea, and congenital hypothyroidism produces a constellation of symptoms that includes problems with both neurological and skeletal development. They actually used to call it cretinism back in a time when people were meaner. That about covers it for some of the effects of T3 and T4, but for these guys, you need to know some of the basic mechanisms of how they operate. Let's start with something really basic. So, why do I keep saying T3 and T4 in the same breath like I can't decide which one I mean? What's the difference? As it turns out, T4 is the primary form secreted by the thyroid gland, and imported into cells where it can exert its effects. But T4 is actually the wimpy version of the hormone. T3 is the real deal. And the target cell is responsible for converting T4 into its more active form by clipping away one of the iodines attached to it. That's what the 4 and the 3 stand for, by the way, the number of iodines attached to the core protein. Speaking of transport, T3 and T4, like cortisol, are lipophilic. What bearing does that have on its transport through the bloodstream? The thyroid twosome has to be carried by a transport protein because they're poorly water-soluble, and that protein is creatively named thyroxine binding globulin, or TBG. TBG acts as a great reservoir for thyroxine, but the only thyroid hormone that can enter cells to exert its effects is the tiny bit that's not bound to TBG. Let's call this guy free thyroxine. But here's where things get interesting, and try to stay with me on this. Say you have a condition where you're low on protein, for example, liver failure. Your TBG synthesis, like the rest of your protein synthesis, is going to tank. So what do you suppose happens to your levels of free thyroxine when the bottom suddenly drops out of the TBG pool? Suddenly, your free pool of thyroid hormone, or your pool of free thyroid hormone, is dramatically increased, which transiently increases the activity of thyroid hormone. Don't worry, it doesn't last long enough for anyone to be symptomatically hyperthyroid, because the additional free thyroxine negatively feeds back on TSH and TRH, suppressing both. So what clinical significance does this have? Well, none really, and that's kind of the point. The feedback suppression normalizes the free T4 levels, and everything's hunky-dory. It does make for some interesting diagnostic snafus. Thyroid panels are pretty cheap, and thyroid disorders are in a lot of differential diagnoses. As a result, they get done a lot on patients who don't really fit the complete picture. Even though the free T4 is normal, what are the total T4 levels going to look like? They're going to look low, even though the patient is not clinically hypothyroid. For those of you who like it concrete, we still have on the screen one active free thyroid hormone molecule, but we lost two of our thyroid hormone molecules because we're down one carrier. It's a good thing to remember when we're doing thyroid tests on individuals with conditions that are known to alter protein values. Some examples to look out for are liver failure, nephrotic syndrome, and chronic glucocorticoid use, which all decrease the body's available protein, and high estrogen states, which increase the body's available protein. That covers T3 and T4's mobilization and action on cells. Now let's backtrack even further and see how it's made. The thyroid gland, if you didn't know, is arranged into follicles, with the surrounding cells that are responsible for controlling the process, and the lumen where all the magic happens. Probably the most important thing to know about thyroid synthesis is what two ingredients are the thyroid hormones derived from. One is iodine, as we mentioned. The other is the amino acid tyrosine. Basically, the follicular cells toss iodine ions into the lumen of the follicle, along with these massive hunks of protein with tyrosine residue sticking out from them. This is called thyroglobulin, and I will seriously hunt you down and slap you if you mix this up with thyroid binding globulin. One's a transport protein, the other's a hormone precursor. That is important. Now here's where the magic happens. Thyroid peroxidase, this wonderful enzyme that hangs out in the lumen of the follicle, does three things at once. First, it oxidizes iodide to iodine. Second, it iodinates the tyrosine residues. And third, it conjoins them to form what basically looks like a bunch of T3s and T4s sticking out of a protein ball. The T4s are made from two diiodinated tyrosines, and the T3s are made from one diiodinated and one monoiodinated tyrosine. Simple addition. So which part of this is regulated exactly? Well, when TSH stimulates the follicles to do so, that massive hunk of thyroglobulin is endocytosed. Lysosomes fuse with the vesicles, lysing the protein component but sparing the T3 and T4 units. These are then secreted into the bloodstream when TSH permits it. Wow, that's a lot of thyroid stuff, huh? Ready to test your knowledge? All right then, it's flash quiz time. Last one of the section. It's been a long section, guys, so I'll keep this one basic. The question is, the thyroid hormone increases metabolism by increasing the rate of sodium-potassium transport. True or false? And the answer is true. This is one of the most important effects of thyroid hormone. You need to know the mechanism by which metabolism is increased. And that about covers it. I hope I showed you a pretty logical way to break this down that you'll actually remember for the test. And that's it for endocrine physiology. Thanks for watching, and if you like the mouth words that come out of my face hole, hit the thumbs up button down below. And as always, comments are more than welcome. Arjun Iyer, signing out.